Today I have a thesis. Today I have a point that I would like to make. If you watch this video, I want you to come away knowing full freaking well that Fn is not always equal to Fg. Okay? Let me show you a couple of easy examples. Let's say we have a 1 kilogram object, a water bottle perhaps, and someone's pushing down on it, and they push down on it with 5 newtons of force. Well then what would the free body diagram of the 1 kilogram object look like? Obviously there would be gravity, which would be 9.8 newtons. There would also be a normal force, of course, because the object is sitting on some kind of surface, a desk or whatever. And then there'd be an applied force of 5 newtons down. Doesn't really matter which way you call x or y. In this case, let's call up y for all you math normative people, and we'll say that Fn minus Fg minus Fa is equal to 0 because the box, the water bottle, whatever, is not going anywhere. Okay, so Fn minus Fg minus Fa equals 0, and therefore we can see that Fn is equal to Fg plus Fa, which is 14.8 newtons, I hope. 9.8 plus 5. And here's a simple example where the normal force is clearly bigger than Fg. One situation. Prove it? Prove it. How about another one? We have an object sliding down a ramp. And let's assume that there's no friction, that the force of friction is equal to 0. Then what is the free body diagram for this object going to look like? There's going to be gravity down, for sure. And there's going to be a normal force. Which way is the normal force going to be? The normal force is 90 degrees to the surface, so the normal force is going to be this way. Now I think you can all agree right off the bat that they are clearly not equal and opposite. So if you're one of those kids who thinks that Fn and Fg are always equal and opposite, then that's another proof that you're not right. And that mistake, by the way, has been made by physics students since Sir Isaac Newton himself. So don't feel too bad if me or your physics teacher yells garbage at you when you say, well, Fn is Fg, so blah, blah, blah. Garbage! Fn is not always equal to Fg. So in this case, I think you can see that if you add Fn to Fg, this thing is going to accelerate down the ramp. That's, of course, Fnet. Fnet has to be down the ramp. So I think, without doing components or any fancy math, this is for grade 11s really, and grade 12s, but you can see, I hope, that Fn would have to be less than gravity, wouldn't it? Because this does form a little triangle, and gravity is the hypotenuse, so clearly Fn would have to be less than Fg in magnitude and not opposite in direction. Again, Fn is not always equal and opposite to Fg.
Fn is not equal to Fg.
Now let's look at a dude in an elevator. We're drawing a free body diagram of the dude. Should we make it a 60 kilogram dude? And let's say that the elevator is accelerating up. Obviously there's gravity. 588 newtons on the dude. What other forces are there on the dude? Because another common mistake in grade 11 is that you guys want to put tension on the dude. There's no tension on a dude in an elevator unless, of course, again, he's hanging himself in the elevator. There's only going to be the force of the elevator floor pushing up on him, which we call normal force, of course, Fn and Fg. And we would say, hey, the y direction is probably up, so we would say Fn minus Fg is equal to ma. We would say the normal force is equal to 60 times the acceleration. What's the acceleration? For simplicity's sake, let's say it's 1 meter per second squared. So 60 times 1 plus 588. And that's 648 newtons, which is clearly bigger than gravity. So again, in an elevator, if it's not at rest and it's not going at a constant velocity, Fn won't be equal to Fg. Now what students still try to do after I've shown them all this evidence that Fn is equal to Fg, they say to themselves, okay, so fine. As long as we're not in a ramp and no one's pushing up or down and we're not in an elevator that's accelerating up or down, then Fn is equal to Fg. But that's still not true. You're trying to find the exceptions. It's a lot easier just to say to yourself, Fn, I don't know what it is. I'll do the math and find out what it is in this case. Because as Mr. Caruana loves to say, even if it's equal to Fg, 99 times out of 100, the one time Fn's not equal to Fg is going to be when? On your test, of course, of course. And now the grade 12s are saying, yeah, Mr. Moran, I know how to do all this. This is pretty easy. But hang on one second. If you understand centripetal force, what about a dude? What about me? What about a 200-pound dude? What about a 90-kilo person just sitting on the earth at rest? Surely Fn equals Fg occasionally, right? Well, but hang on a second, because this dude only has gravity and normal force. But the guy is on the surface of the earth and going in a circle around the earth every day. So really, there's a centripetal force, isn't there? Really, Fg minus Fn has to equal mac. So even you and me sitting on the surface of the earth right now, we can see, I think, that Fn is equal to Fg minus 4 pi squared mr over t squared. The radius of the Earth is something like 6.4 times 10 to the 6 meters. And of course, the period of its rotation is 24 hours. So we can see that Fn is going to equal on this guy 90g minus 4 pi squared times 90 times 6.4 times 10 to the 6 divided by 24 times 3600, because that's how many seconds in a day, squared. So we can see that even in a situation where someone's just standing at rest on the surface of the earth, the normal force is going to be equal to 880, what did I say, 882, plus gravity, 882, minus about 3 newtons. So it's 879 newtons. So even for the skeptical grade 12s who say, yeah, this is easy, Mr. Moran, I would argue that Fn is almost never actually equal to gravity. And I think I've proven it.
Fn is not freaking